everyone. Thank you for joining today's webinar we have going on right now. Feel free to tell us where you're from in the chat and what you can see yourself 3D printing. It'd be awesome to see kind of what brought you guys here today. So we're going to do a workflow on SLA 3D printing today in today's webinar. Kevin is going to do a great job speaking on this subject. We're going to look at how you can achieve tight tolerances with robust engineering materials. So specifically, we're going to look at several engineering applications that have demanding tolerances and really take a deep dive into those materials and what you can learn from them. And Kevin's going to go through that. So traditionally, you might be used to lots of CNC setup, work loading, programming, and the labor behind that really gets expensive over time because it's very time intensive. And there's other technologies out there as well, such as FDM and DLP, and they can be quick, but they're not always precise. So they might not be actually useful for what you need to specifically do. So after today's webinar, you're going to actually be able to achieve demanding tolerances easily in your workspace using stereolithography printing. You're going to have less waiting time, and you won't have to outsource at all. This will all happen in-house. And it's also going to be cheaper for you thanks to the material costs. And overall, there's a small footprint involved with this. It's intuitive, and it's very convenient for you to set up and start doing today. So we have an agenda here we're going to quickly go through. I'm going to introduce you to Kevin. We're going to look at what's possible with SLA technology. And then we're going to look at how does stereolithography actually work. And we're going to take a deep dive on the 6 different materials that we have today that you can use. And then this is really cool. This is my favorite part probably. We're going to look at the workflow, kind of the entire printing process and how it visually looks. It's a hands-on approach. And if you stay on until the end, we're going to give you a special offer because you joined today's webinar and specifically in how you can get started in printing today. And we'll also have a time for questions and answers at the end. So right now, if you can look to your right, there's a Q&A box. At any moment in the webinar, feel free to type your question in. We will be reviewing them and getting to them at the end. And if we can't, we will always follow up with an email afterwards. So feel free to type away while the webinar is going on. So Kevin, I'm going to hand the floor to you.
Thanks, Ferris, and everybody for joining today. Excited to be here and excited to talk to you guys today about stereolithography 3D printing. We already went over the agenda, so we'll just jump into a little bit of an introduction about me, and then we'll start going through the slides here. So my name is Kevin Gautier. I've been with Formlabs for a little over 4 years now. I am a channel application engineer and also work on our business development team. In my spare time, I actually sponsor a Formula SAE team, which is Kennesaw State University Motorsports. And you can see here a picture of us actually working on a carbon fiber intake manifold that we actually molded on Formlabs printed parts. So you can see here the team all working on doing this carbon fiber layup. I also like to build electric vehicles and other sort of robotic projects. And of course, really enjoy working with Formlabs 3D printers and CADing and producing parts digitally. So an introduction to Formlabs, we make professional stereolithography 3D printers that fit on your desktop. Our goal was really to make this technology accessible and very scalable. So we sit in between low-cost consumer fused deposition printers and high-end industrial 3D printers, and we like to call ourselves industrial quality on the desktop. The software is always free. We have a wide range of materials available for the printer, and the printer is at a very affordable price point, starting at around $3,350. We have lots of really large customers. We'd love to share all their stories at some point, but those stories are typically difficult to get out of them. So you can see some of those brand names right here, but you can see how wide and how vast this the use cases may be. Everything from robots to cars to dental surgical guides and different customized in-ear monitors and other products that can be customized to the human body. So lots of really cool stuff going on, and these stories will come out over time, hopefully. So to get started here, let's look at what geometry is actually possible with stereolithography 3D printing. You can see sort of the minimums here. So this is like the thinnest sort of wall you can print on the left side with supports on both sides. So this is an encapsulated wall. the minimum wall with no supports on each side. You can see it's a little bit, has to be a little bit thicker at about 600 microns or 0.6 millimeters. This is because it needs a little bit more rigidity to sort of support itself without having any geometry on the sides. Unsupported overhangs, so it's really convenient with a stereolithography 3D printer that you can actually get away with a little bit of unsupported overhang. This is great if you're going to try to emboss any text, or you just have fine details maybe around a character sculpture or something like that that you'd like to be able to preserve without having any support structures under it. So you can have a little bit of an overhang. You can also print parts with no supports under it at about a 20-degree angle or 19-degree angle, which is really convenient when you start setting up models in preform. And we're going to take a look at an example of setting up a model in preform and then actually taking it to completion later in the presentation. Fine detail, so you can see you can emboss detail down to about 100 microns. You can engrave down to about 400 microns. This is also true for internal passageways. You can do like microfluidic devices or any sort of internal channels down to about a 0.5 millimeter internally. So that's similar to this spec right here. Minimum hole size, 50 microns. Minimum drain hole size, 3.5 millimeters, about 1/8 of an inch. The reason this drain hole is important is on some geometry you actually need to evacuate air pressure, and we can take a look at that in the preform software when we get there later in the presentation. But if you do have a sealed off geometry where you actually need to be able to vent air pressure and then also use that hole to wash out the part later, you need about 3.5 millimeters or 1/8 of an inch. So how does stereolithography 3D printing work? You can see first, before we actually start on like how the printer itself works, you can see a couple of different examples of the same part printed on different technology printers. So fused deposition here on the left, moving into stereolithography here on the right. So it all starts with a resin tank, which is the item here on the left, and a resin cartridge, which are these items here on the right. These are the raw material and how the raw material actually gets shipped to the customer. Once the resin cartridge gets to you, it actually gets and put in the printer, it actually gets dispensed from this cartridge into this tank, and we'll look at that in the video later. After resin's been dispensed into this resin tank, the build platform is actually lowered down into the resin tank. This is the build platform. This is where your part will actually be attached during the printing process. A laser is bounced off 2 different moving mirrors. These mirrors are mounted to what's called galvanometers, and they drive the laser light around in the X and Y axes. Together, they work together to actually draw out a 2D cross section of a part. And once they finish drawing out that 2D cross section, the build platform moves up, and then you can start the next layer. Those layers can be either 100, 50, or 25 microns thick. Once the part's complete, you'll see it looks something like this. This is a part sitting on support structures here. So these support structures will get removed. And again, we'll look at that process later in the video. So using stereolithography to achieve tolerances, and why is a laser-based machine important for achieving these tolerances? So we're going to look into that into some detail. So first, just a refresher: accuracy, precision. You can see the difference in accuracy and precision here on the left, and then some examples of the opposite of those things here on the right. So accuracy is how close a measurement is to the true target value. And precision measures the repeatability. So this is how consistent are you at the shots that you take. And this all comes down to what sort of fit are you trying to achieve. In engineering, there's 3 major types of fits. There's clearance fits, which move completely freely. This would be like a simple pin in a hole that slides together really easily and spins. A transition fit, this would be kind of like a peg and a pegboard where it takes a bit of force to push the peg into the hole, but and that is enough force to actually hold that peg in that hole, and you can still disassemble that part relatively easily. And then an interference fit, this is commonly referred to as a press fit. This is no movement, and it really resists the force. It takes a lot of force to push it together and also a lot of force to pull it back apart. And you can see sort of how you accomplish these fits by defining how the tolerance zones interact with each other. So a clearance fit, these tolerance zones are going to be completely clear of each other. In a transition fit, the tolerance zones begin to intersect. And in an interference fit, the tolerance zones fully intersect each other. So we can see a little bit of a diagram here of how this works. We can use the peg and a hole example and continue with that. So this section here and here is a cross-section cut of a hole, and then you can see the hole in this section, and then the shaft over here, and where these tolerance zones actually are and how they interact with each other. So you can see clearly here, this would be just a slip fit. As these tolerance zones begin to come into each other's range, that's when the fit starts to tighten up. So to put some data behind what we're talking about, this is a sort of real world test on a 10 millimeter peg and close to 10 millimeter holes. They vary in size. You can see the different sizes here on the left. That data is plotted against this chart, so you can see what CAD, sort of tolerance you model into CAD software, and what the outcome is when it comes to the fit between that peg and that hole. So you can see your interference fit is in sort of the negative to 0 range. Transition fits come in from 0 to about 0.375 millimeters, and clearance fits happen at about 0.05 plus millimeters. So about 50 microns modeled into CAD software is going to get you a full clearance fit. And you can see this is for our tough resin. We're going to talk about all our different resins in later slides, but we're going to talk about this specific test here in 2 different resins. So tough resin, you can see the results here. And then durable resin, pretty similar. Main difference with durable resin is it's got a little bit more elongation to it, so these ranges are a little bit wider than they are with the tough resin. That's a little bit more, a little bit less elongation in that tough resin. So why can laser-based stereolithography 3D printers achieve all these fits, but other technology stereolithography 3D printers like DLP or LCD printers, why can't they? So we're going to take a look at that in the next few slides. So first, it comes down to how the 2 machines actually work and how they form curves. So laser-based stereolithography machine like the Form 2 actually uses an X and Y galvanometer that can feed at the same time. That way you can actually draw a smooth curve with the 2 lasers working together in unison. With something like a DLP or an LCD based printer, you're using pixels to define the curve. So you can see that the software has to decide if a pixel is going to be turned on or off in order to accomplish this curvature. And this means that you have to snap to the nearest pixel, whereas with a laser-based machine, you can sort of just move the laser a little bit further. And we're going to take a look at what that looks like in the next couple of slides here. So just for an example, we're using about a 1 millimeter peg, actually a 0.9 millimeter peg. And you can see the left and the right. The left is how a DLP or an LCD printer is going to form the peg. So you can see our 0.9 millimeter diameter here. And you can see each pixel is about 50 microns, which is a good sort of industry sort of standard when it comes to DLP and LCD projector machines. There's some that are lower, some that are higher, but 50 microns is about an average. And you can see while the software is deciding how it's going to draw this cross section, it's going to turn pixels on or off depending on if they're in the boundary or not. So in the 0.9 millimeter shaft, clearly these 2 pixels would be turned on, and then the software decides which other pixels are going to be on, probably by how much of the pixels actually filled. So this one would probably be on, this one would probably be on, this one would probably be turned off. Regardless, it uses these series of pixels to draw this circle. And you can see on the left, or I'm sorry, on the right here, you can see how the circle is formed on the Form 2. The dashed line, the construction line, is actually the laser path. The diameter of this circle right here is the diameter of the laser point, so about 150 micron diameter. So you'll see that the path that the laser would take to make this outer diameter here is 750 microns, 0.75 millimeter diameter. And if you were to change the size to say of the peg to say 0.95 millimeters, you can see where the problem starts to happen. So we'll just skip back to the 0.9 millimeter. You see we're right on the edge of the boundary. You go to 0.95, now you're halfway through the boundary, or halfway through the next pixel, and the software is going to have to decide which pixels are turned on or off. And you can see why this starts leading to some challenges for the printer being able to accomplish sort of that that difference in fit between an interference and a transition fit, mainly because it can't actually make half a pixel. So in the case of the Form 2, we'll just increase the laser path by 50 microns to produce a slightly larger 0.95 millimeter peg versus a 0.9 millimeter peg. But with a DLP, it can't quite do that. So laser-based SLA 3D printers really can achieve a larger range of tolerances due to the fact that they don't have to snap to these individual pixels. And this has all been a very basic example with just a simple peg. But when you scale this to some 3D geometry, you can see what really happens. With a laser-based machine, since you can make these sort of fine steps, you can achieve really smooth surface quality. With a DLP machine, since it has to determine if a pixel's on or off, and you can really see it sort of in this area right here, you actually see an artifact left over from when the printer decides to change over and turn a pixel on or off. So it has to print a few layers with, say, this pixel turned on, and then after a few layers, it has to snap to the next pixel, and that's what leaves sort of this more vertical artifact into the part, where in a laser-based SLA part like ours, you're only going to see horizontal lines from the actual build layering process during the build. In a DLP or LCD part, you're going to see those horizontal lines from the layers, and you're also going to see more vertical lines and this sort of scaling from the printer deciding if it's going to turn pixels on or off. So we'll go through each material for the printer and each engineering material. So first, just a matrix of all of the sort of engineering materials. So standard, tough, durable, high temp, rigid, and gray pro. And you can see them all sort of outlined here. So if you're looking for something with really high impact strength, you'd be looking towards our rigid resin. If you're going to look at if you're looking something for high temperature applications, you would look at our high temperature resin. This is just a good way to like globally look at all the resins all at once. And we're going to go through each one of these individually. So starting with the tough resin, and I've actually got a sample of tough resin here. This material is really great for any sort of situation that you want to simulate something like ABS plastic. It's got some flex to it, so you can see we can actually make a working snap fit here. And it springs back, which is really convenient. It's really good for sort of general prototyping of things that are going to be maybe impacted or need some flex to them. Our standard resin, like standard clear resin, is going to be more brittle and won't really allow you to do things that sort of move and snap together like this part we're looking at. See sort of some of the examples for tough resin. So we see it used for jigs and fixtures, different work holding applications. This is because it can sort of resist the impact of the tool coming into contact with the part and applying some shock to the part. Different sorts of brackets for assembly lines. I've seen it used for troughs for components to sort of slide down on an assembly line. Different sort of assembly fixtures and work holding. In consumer products, we've seen it used for prototypes of in-use products, and then all sorts of different mounts and brackets in the entertainment and TV production industry. Durable resin looks like this. It's similar to polypropylene plastic. What's really unique about the durable resin is it's got a really high impact strength. It's also it also resists abrasions to itself. So most all the other materials actually scratch themselves. If you sort of scratch two parts against each other, they'll scratch each other. But the durable resin is slick and does not abrase itself. So I'm rubbing two durable parts against each other here, and you can see there's like no dusting or any sort of scratching happening. So this is great for anything that needs to slide against itself, things like hinges or any sort of sliding joint like a piston in a hole or a pin in a hole. Really good for sliding things. Since it's also really got a really low modulus and high impact strength. It's good for any sort of living hinge application as well. So it's got good flex to it. You can build things like this tissue box that actually have a um, fully living hinge, which means this tissue box doesn't have an actual mechanical sort of pin and hole hinge. Instead, this is actually just a flexible joint, and the whole thing will flex over itself and close. So prototypes of packaging, different sorts of bushings because it's good for things that slide against each other. Um, Prototypes of finished polypropylene parts, and I actually really like to use it for making gears because of the fact that it doesn't abrase itself. So here's an example of a gear I actually printed in durable resin, and we'll see what this gear actually goes into in future slides. High temperature resin, it's got a heat deflection of 289 degrees Celsius, which is the highest heat deflection temperature in the plastics 3D printing market. We initially designed it for things like prototypes of injection mold tools, or actually making low run injection molding tools. You can see that example there in the slide deck. I've also got one here. Also got a torch tip done in high temperature resin. So it's really good. It's really good for under hood applications if you're going to build maybe an enclosure for a data logger or any sort of component that's going to be in a really hot environment, like under a hood of a car or in some sort of manufacturing process. I've got a customer actually using it to make some brackets that's going to go in a manufacturing line that's really hot. In the composites industry, I'm starting to see this material be used for making master patterns or even induced molds, 3D printed molds for making composite parts. We've seen it used for fluid flow testing of like hot fluids through manifolds to see how those fluids sort of flow through the parts, different sorts of valve bodies and that sort of thing. And then I think one of the main uses of the material is for packaging and prototypes of packaging using the vacuum forming technique over a high temperature resin printed mold. Next material is our rigid resin, and here's a piece. So rigid resin is our first resin that's actually reinforced with glass fiber. So this is really stiff material. It's great for anything that's going to be thin wall. So if you're trying to produce a prototype of something that might end up being sheet metal or composite or something that's going to be thin, it's really great material for that. It doesn't deform at all. It's insanely rigid actually, and it's got a really nice sort of ting to it because of that glass fill. The finish is really incredibly smooth too. This material is quickly becoming one of my favorite materials for anything that doesn't or anything that needs to resist any sort of deflection. You don't want to try to sort of bend this material at all because it will crack instead of deflect. So really good for that. Also really good for anything that needs to hold its geometry over time and not deform. So we see it used for electrical devices, sort of electrical connectors, enclosures, and housings for sensors, and air handling, things like fans because they're really fan blades because they're really thin, or even enclosures that go around fans, or different sort of airflow manifolds, and different and sheet metal prototypes of sheet metal parts because it can actually achieve those really thin wall sections. Next is our Gray Pro material. This material actually has a similar base material to the rigid resin, just without the glass fill. So this material is very precise. It's got moderate elongation and resistance to deformation over time, just like the rigid resin. The main difference is without that glass fill, it's got a little bit more flex to it. This you could probably make a snap fit with this material. Really tough resin's a little bit better for that because it elongates a bit more. But the Gray Pro material is going to resist the deformation over time much better than something like tough resin will. So there's there's a decision to be made about which one of those resins is better for your application. And any of our application engineers and our salespeople can help you pick the correct material for your sort of use case. But Gray Pro is quickly becoming one of my more favorite resins. Some of its use cases are parallel to tough. Things like prototypes of products, form and fit testing of different components in sort of machine shops or manufacturing environments. But really the drive home point to the Gray Pro resin is its ability to be used in long-term use cases, long-term applications, because it resists the deformation over time. Flexible material. This is a rubber-like material that's a 80A durometer, and it comes in this sort of black color, and you can see this boot here and how flexible that is. Also, I have a sample here of varying sort of thicknesses. So it starts at 1.5 millimeters over here. Then it moves to 3, 4.5, I believe. Yeah, 4.5. 6 starts getting pretty rigid. And then at 7.5 millimeters, you can see it's starting to get really, really rigid. But either way, about 80 durometer, really good color for different applications like grips on tool handles or prototypes of overmolded materials for consumer products, that sort of thing. Pretty cool material to work with. We see it used for, like I said, prototypes of overmolds. So this is like rubberized components over injection molded parts, mass customized wearable items, stamping, making different stamps that are like actual ink stamps you can do with this flexible resin, and then different grips and handles on tools. So now we'll look at the 3D printing workflow and how you actually take a part from a concept, an STL file, and take it all the way to completion. So we're going to start in our preform software by making this component here, which is half of the case of a 90-degree angle drive. The gears we looked at earlier in the presentation actually fit into this, and we'll see them in the demonstration we're going to do here in a minute. But yeah, this is our preform software, so you can navigate around in 3D and look all over your build volume. You can get your bearings here. This is the front of the printer. This is the wiper side of the printer. Use a right mouse click to sort of move them all around in 3D. Center mouse wheel to pan. And you can move the model around, and look at it. Some of the features that are important on this part that we want to be thinking about are its critical surfaces and how it's going to meet up against its mating component, the part that goes right next to it, so the other half of this gear case. So really our most critical tolerances are all on this side of the part. You can see this lip here. This is a critical sort of surface because it has to fit up against the negative lip of the other side of the part. Also, we've got our bearing bores here, so those are clearly important. Where we're going with this is we're sort of eyeing up on the part and figuring out, what this part's anatomy is and which side the support structures really need to be on, because you can't print the part just like this. There's nothing holding this part down over here, and there, you need support structures under here. So regardless, we're gonna pick the best orientation for making this part and then actually send it over to the printer and watch how this part actually gets produced. So I always like to think about 3D printing parts a lot like machining parts, and I want to care about the artifacts the machine leave over in the end and make sure that they're going to look good on the part. And since this is a 90-degree drive, I always think it's a good idea to have my layer lines running 45 degrees through the part. I just think that gives you symmetry from the left to the right side, gives you the same infill patterns from left to right. So either way, I just think 45 degrees is a really good way to orient this model. So that's the first step we're going to do. We're going to start in the orientation tab, and we're going to orient this model at 45 degrees. So I simply typed 45 degrees in Y, and now we've got the part sitting down at 45 degrees. The next thing we want to do is, if you remember back to the slides on the geometry, about 20 degrees is a good number for ensuring that the printer can print things without overhangs. So you can see in some of these areas we've got some pretty solid overhangs. So I'm actually just going to tilt the part back at about 20 degrees. And that'll open up all these spaces. And now we have really printable geometry in this orientation. You can start looking at what the layers sort of look at with the slider over here on the right. So you can manually just drag the slider up and down and look at what each individual layer looks like. You can also use your page up and page down button to go one layer at a time. One thing that's interesting about page up and page down and going one layer at a time is if you zoom in really far, you can actually see the tool paths that the printer is going to take. So you can see these are the infills, and then we do a couple finishing passes around the outside to make the outside really smooth. And then there's actually one last just small step over to just clean up the edge of the part and make it look as good as possible. So the last sort of path the laser will take is this last line here, just to clean up the outside of the part. What's interesting about looking at it one layer at a time is you can see we actually do a crisscross infill. So I just switched from layer 394 to layer 395, and they just go 90 degrees each time, and we get that crisscross infill, which gives us really strong parts. So this is the orientation that we're going to use to print this part. Next thing we're going to need to do is actually generate support structures under the part, so we have something attaching it to the build platform. So we'll just skip down to the support structures tab. And in the support structures tab, you have some options. The two main options we'll talk about today are density and point size. So density defines the number of points you're going to have. Point size defines how large the diameter of the point actually is. By default, these points in tough resin are typically a bit larger. They're usually about 0.7 millimeters and a 1.0 density. I've been able to reduce those a little bit on this part down to the numbers you see here, 0.9 and 0.55, mainly because the cross-sectional area of this part is not very large anywhere. It's a shelled out sort of thin wall part, and that means we have pretty low cross-sectional area, so we don't need quite as much support hanging on to it as something that would be much more blocky with a lot more cross-sectional area to fill and resist during the peel process. So that's the density and support size we're going to use, and we're going to go ahead and generate these supports. While we're doing that, I'll just explain a couple other things. We've got some advanced options in here that allow you to tweak the supports even further. Things like define how thick the base is, how high the part is off the base, that sort of thing. Don't really need those options for general purpose printing, especially with this part here. But those are some those are some features we've enabled for more power users. So we can see that the support structures have now generated. And I like to go through and manually look at them and maybe do some manual cleanup of support structures. So this support structure right here, for example, is in a critical surface where we don't really want it. And so we want to get it out of there. So I'm going to click Edit All. And then I'm actually just going to remove that support structure. That one's important to our fit, so I don't really want a support point there. Same thing with this one. Going to get all support points off any critical surfaces. So that's good, and we'll just apply those edits. Next thing is clean up any redundant supports that are just really unnecessary. Once you start getting to sort of more vertical faces, you really don't need supports running up the sides of them. There is an advanced feature called slope multiplier that will reduce supports up a slope like this, but I'm just going to do them manually. So I'm going to click Edit All again, and then I'm going to take the top 3 supports off both halves here. And then these aren't quite symmetrical, and I always like to be symmetrical, so I'm going to come in and actually just rebuild these 3 supports myself here and get them symmetrical. So apply those, and that's looking pretty good. Overall, this part is about ready to print. I think actually I can remove a couple more right there too, so I'm going to do that as well real quick. So we'll remove these 2 and these 2. Hit apply. So this part's good to go. After the supports are done, you're going to select where on the build platform you actually want to print the part. So I just moved down to our layout tab. In the layout tab, you can also make copies of parts if you want, with the supports already retained, so you don't have to re-support the part. Things to note is what orientation you want to print in and where on the build platform you want to print. So that's what we're going to talk about. If you were to bias the part towards the wiper side, it would print slightly faster because the wiper only has to go as far as the part. It wouldn't have to traverse the entire build platform. So that's one sort of rule, or one sort of piece of advice. But I will say that it's fairly important to think about which direction the Form 2 peels in. So the Form 2 is going to do a slide and peel, and that slide goes in this direction, the direction of the wiper. So if we were to leave the part as is, the part would actually be getting sort of some torsion on it, trying to kind of peel the part off these support structures in the left to right orientation. So all that force is sort of divided across this much width. If we were to rotate this part 90 degrees, then we're actually distributing the load over a lot more area here, over a lot more support points. So this is the direction you really want to print this part in, so that side load is divided across the whole width of the part. So we're going to actually print it in this orientation. And the last thing is just deciding where on the build platform you want to print the part. For this part, this doesn't really matter. For users that use their printers a lot and are really trying to maintain their resin tank, they're usually conscious of where they print on the build platform, and they use different areas. That way they get more life out of their resin tank. So for this though, we'll just go ahead and stick this part right here. And then you simply send the part over to the printer. You can see my printer's name is Unknown Loris, and it's already set up with Tough V5 resin in its resin tank and a cartridge of Tough V5 resin, even though the cartridge is quite low right now. And then we would just send the print over to the printer by clicking upload here. So that's how that workflow works. Once the part's actually sent over to the printer, then we print it out, and I'm going to show you what that process looks like now.
Okay, so we saw in the previous slides the resin tank, build platform, and resin cartridge. Now we're actually going to put those parts in the machine and kick the print off. So I always like to start with the resin tank. That's going to protect this piece of glass here in the printer and make sure that no resin were to drip down from, say, the build platform onto the piece of glass. So resin tank is going to go in first. And you can see here this resin tank is already filled with tough resin. I usually like to give the resin a couple swipes with the wiper just to make sure it's all stirred up. Also to make sure that the bottom of the tank doesn't have any cured resin on it, so you can see the bottom of the tank is very clear here. This just ensures your resin's in good shape and ready to be used. We'll take the resin tank and put it into the printer. Remember from the slides there's 4 little holes that the tank drops into, so you can kind of feel them. Push the tank downward and backward into the printer and you'll kind of feel it click in. And you can see it says resin tank inserted with Tough V5 resin. Next we're going to put the wiper in, so there's a little carrier for the wiper to snap into, so we're going to find that and then set the wiper down into the slot and push backwards. You'll see that the surface goes flush here at the front once the wiper is pushed into place. Next we'll put the build platform into the printer by lifting the release lever here, pushing the build platform into the printer until it sort of clicks, and then closing the lever. Now we'll close the printer up. We're done inside the machine, and we just need to install the resin cartridge. Remember, we're using Tough V5 for this part. We selected that in preform. This is the cartridge. If you haven't shaken this already, you're going to want to shake this for up to 2 minutes. The other thing I like to do is check the bite valve here on the bottom and just make sure that it's opening properly. Sometimes they get stuck, and if you manually work this with your finger, you can ensure that's not going to happen once you put the cartridge in the printer. So just make sure that's opening up, and then go ahead and drop your resin cartridge into your printer and pop the air vent valve open. Now the printer is assembled and ready to print, so all we have to do is select the model we want to print, the preform file we sent over earlier. This is the 90-degree driven node, so we're going to select that print, then click print now. The printer is going to initialize. Right now it's just reminding us to make sure the vent cap is open, which we just did, and to make sure that there's a build platform in the printer, which there is. So we're sure of all of that, and we're going to push confirm. Now the printer is going to go through a couple steps and initialize. It's also going to heat the resin up to about 35 degrees Celsius before it starts printing. So you'll see it says preparing to print. It's going to do a couple motor moves, and then the screen will come up saying we're at about 31.7 degrees Celsius, so it's going to heat up from there to 35. It's also filling the resin tank and ensuring that the level of resin in the resin tank is appropriate. So once it finishes all of these steps, it'll begin the print job. Okay, so our part finished printing, so we're going to go ahead and take it out of Form 2. And we can see what the part looks like raw out of the printer. It looks really, really nice. Now we're going to need to go ahead and wash and cure this part. So we'll start in Form Wash by popping the Form Wash open. And you can see there's actually a mount for the build platform right here. So we'll install the build platform into Form Wash. Then go ahead and start the 20-minute wash cycle. While Form Wash is running, it's going to actually agitate isopropyl alcohol and wash the part. It actually is going to reverse directions every once in a while, so alcohol flows around both sides of the part. Once it's done washing, we'll actually move it into the cure. The cure takes a little time to heat up to 60 degrees Celsius. We're going to do a 60-minute cure at 60 degrees Celsius. So I usually like to start preheating the form cure while the Form Wash is running. And we'll come back in about 20 minutes, remove the parts from the build platform, and move them into form cure. Okay, so the parts just came out of Form Wash. You'll see they're dripping isopropyl alcohol, so we'll let it drip for a little while, get most of that isopropyl alcohol off there before we take the build platform out of the Form Wash. Once it's done dripping, I'm going to go through and just start spraying a couple little areas that might hold isopropyl alcohol. We'll take a look at that in just a second once it stops dripping. Okay, so the parts have stopped dripping and you can see they're actually starting to dry quite well. So we're going to take the build platform out and just take a look around your part. I like to see if there's any areas that might have trapped some isopropyl alcohol. Critical areas to look are usually in holes or down in little crevices. What you're going to want to do with those is make sure you blow any liquid isopropyl alcohol out of any areas where it might have gotten trapped. I use canned air for this. You don't want to use shop air typically because it might have some water or some oil in it and that'll leave spots in your parts. So I like canned air for this. And this part has like a little areas in here where it might trap a little bit of resin, or I mean a little bit of alcohol. So we'll just go ahead and give a little spray in those sort of areas, maybe down in some of these holes. So make sure we've got all the alcohol out of all the holes. Any like tight corners like this can sort of trap a little alcohol, and you can see it probably spraying out of there right now. So I just like to go around all these sections, just make sure I'm not leaving any areas where there's liquid alcohol and resin, because once that goes into form cure, that resin and alcohol will actually cure in place. So we want to make sure we get it off there and it's dry first. So I'm going to set the build platform down on the table here, and we're going to start removing the parts. First thing I'm going to do is actually put the Form Wash to sleep. For part removal, everyone's got a different technique. I like the scraper that comes with the Form Wash actually, and my technique is to actually get under the part and then use a little twisting action to get the part to release, and you can see how easily the part comes up when you do it that way. And then I just usually work around the perimeter, and you can see the part coming up as we do that. What you're trying to do is get an area where you can actually get the scraper up under the part, just like that. And this one's released. And then we'll go ahead and get the other one released. Another note is you always want to handle the parts by the supports of the bases. Try not to touch the parts because you will leave fingerprints in them if you touch them when they're still a little bit wet like they are right now. Once they fully harden, cure in the form cure, no worries about fingerprints anymore. So yeah, I'm just working my way around this part right here. Form Wash is really nice because it washes your build platform too, so I'm not actually touching liquid resin right now, which is nice. So I've got both parts released from the build platform, and now what I'm going to do is actually move them into form cure, which I already have preheated. So we can see it's actually been running. So what we'll do is just reset the timer once I move the parts into form cure. And I like to do this pretty quickly so I don't lose temperature. So we're just going to open up form cure and then put the parts in. Then we'll close form cure up and it'll actually resume. Like I said, I'm going to edit the program real quick and make sure I set it back to 60 minutes. So we do a full 60-minute cure. And you'll see the temperature is coming back up. We lost about 4 degrees Celsius when I opened up the form cure, but I'll come back in a second once the lights are on and you can see what that looks like. Okay, our final step. So we've got our parts out of the form cure now. You can check them out. They look good. They're bone dry to the touch. No more worries about putting any fingerprints or anything like that in them. And now all we have to do is remove these support structures, which people do a bunch of different ways. For me, it really depends on the type of model I'm doing. For something like a larger sort of engineering part like this, really I'll just be removing these supports in bulk, and you can see if you actually fatigue them a little bit, they kind of just break right off. The only thing to really note when you're just sort of breaking them off is that the support points will scratch the part. So you should think about which way you're pulling on the supports, and maybe remove supports manually with some clippers in places that could end up dragging across the part and scratching it up. If I'm doing something really delicate and small, like a mini figurine or a character of some sort, I might actually go in and clip the supports kind of long, sort of out here in this area, and then actually come back with an X-Acto knife later and clean them all up really nicely. This really just depends on the type of model and how large it is, that sort of thing. For this model, like I said, for the most part, I'm going to be fatiguing and breaking the supports off, and you'll see kind of the process I take. So I'm going to start sort of at this end of the part, and I'm just going to clip the base so we can remove that part separately, and you can see the whole thing just fell off there, which is great. And there's just very little amount of mark left from the supports. So we're just going to go through the whole part with that sort of mentality and get all these supports off here. So I'm going to crack the base in a few places. And then I'm just going to start looking at how these supports are formed and just start sort of fatiguing a couple of these, breaking a couple of these out of the way. And it's all looking really good so far. Remember, I'm trying not to scratch the part with supports, so I'm kind of pulling away from the part as I remove the support structures. And you can see there's very little support artifact left there. I'm just going to keep removing these little sections until I've got this part completely clear of support structures. Sometimes you get little areas like this that are kind of difficult to get off, and I might just come in here with some clippers and clip, get that out of the way. And there you have it. You've got a part with all its support structures removed. This is actually really smooth already. A couple little rough edges. Like any sort of manufacturing process, you can actually go back and do any sort of secondary post-processing steps you might want to do, like sanding, which is definitely an option for a part like this. But overall, you can see really when you fine-tune your support structures, I used about, I think I used 0.55 millimeter supports on this part at a 0.9 density. As long as you're not way over supported, the supports come off the parts like really easily. Same thing will happen with this part. So now we've got the support points removed from both halves. I can show you how this whole assembly works. So here's our two halves, and you can see how nicely they sort of fit together. And you probably remember from preform, there's an inner and outer lip that actually has to fit together. So we can see that lip here. And if we just line everything up, it really just fits together super nice, showing how you can achieve those tolerances with the printer. Now I'm going to walk you through the rest of the assembly, and we'll put this whole gearbox together and see how it works. So a couple of gears printed in durable resin with a interference fit to make a nice press fit into these bearings, which I got to get aligned, and then just push these together. Same thing with this one. And these will actually get assembled into this gearbox. So one half here, and the other half here. So we've got the two gears assembled, and they run nicely together. The second half of the gear case goes on. Nice snug fit. And we'll actually just put Plastitite thread forming screws in, which I'm gonna just start by hand. I'll come back and tighten up. So we got our thread forming screws in, holding the two cases together. The gear still runs smooth. Last thing is our retainer cover that also keeps the gears pushed back into place. These slightly larger screw heads, so hopefully, I don't need to change bits here, but let's give it a go. Yep, this bit's gonna work. We've got a retainer plate on that's holding those gears back. You can see there are square drives down in here, which are where these two drive shafts go. So we slide a drive shaft into here, and another drive shaft into here. And now these turn each other, and this is what actuates the inside frame of the rotor casting unit that we're going to take a look at in the next slide.
Hope you guys enjoyed that demo. One thing I wanted to recap on in preform real quick, I noticed that we actually had a printability issue on the model that I prepped during the live demonstration, and I thought it'd be a good opportunity to explain that to you. So you can see this red sort of cross here says I've got one unsupported minima. So I'm going to turn this switch on here, and it shows me where that unsupported minima is. And actually, it's right here in this area. What happened was I just put this lower support just slightly too low. So we can go back to the support tab, edit, and then actually just move this support over to here and apply that edit. And that'll clear up that unsupported minima. That's just one of the consequences of doing a live software demonstration. But either way, that should totally fix that. I also heard in the questions section quite a few questions about the red areas and the sort of amount of supports you can use. So it's something you really get a feel for the more you use the printer. I would say the first time you print something, you'll probably be scared and don't want any red at all. And then the more you print with a printer, the more red you'll sort of have showing. It's not a really easy question to answer, but I'll try to do my best here. The best way to explain it is, in my opinion, to look at the what the printer is actually trying to print, to look at these cross sections. And before I print anything, I'll hold page up and watch basically a video of this part being printed. And I look for areas that are alarming, that tell me like there's no way it can print that. Basically things that are going to be paper thin, or not have enough support under them. You can see these there's actually one, five, six, seven. There's 7 bodies being formed right here right now. So you need to make sure each one of these bodies has a support point under it. So you can see that like little sliver being formed right there. You can see each of these little islands has a support under it. That's what the unsupported minima was all about. Basically, before we moved that support point over, there was a little section that wasn't being supported. So this support point was just too far over, for example. So you're just making sure that all your minimas are supported, and you're making sure that the geometry that the printer is trying to print, these cross sections look like something that could feasibly be printed. And that's really the best way I have to explain it. It's a little bit abstract at first, but once you use the printer and print a few things out, you start getting really comfortable with what the printer is capable of printing. So we'll move back over to our slide deck. And we can see sort of the end, the full wrap up here. So this is the part we actually printed, and you can see how well these two halves actually fit together. You can see the gearbox is assembled here. And then all of these went together to produce this rotor casting machine. And the part we printed was actually this corner section right here. So in conclusion, We learned how laser-based stereolithography can achieve all 3 types of engineering fits. We saw that the printer can produce a wide range of geometry. There's 6 engineering materials to enable your applications. And we saw the simplicity of the start to end printing process. So now I'll pass it back over to Ferris to take this home.
Thanks, Kevin. That was really wonderful. That video you showed was also just amazing. Especially jumping back into preform right afterwards and seeing how the unsupported minima was caught by the software automatically was pretty cool. Just a slight difference, and the software knows right away and can help you out without actually messing up an entire print afterwards. I think that's pretty valuable to do. So yeah, thanks for showing all that. So earlier on in the webinar, we told you that we were going to teach you about SLA printing and how it works. Teach you about the applications and the engineering materials that are required for it, and how you can really achieve demanding tolerances doing all that. And I really hope that you now feel a little more comfortable approaching the subject and can maybe get started on SLA printing for your use.